let's talk about magnetism. All right, so the symbol for magnetism is what you would expect it to be. It's the letter B. It is a vector. This is the symbol for a magnetic field. Now, there are some textbooks that will use H for the magnetic field and refer to this as the magnetic flux density. I believe that's the terminology, but B is what we'll be using for magnetic field. And just side note, the difference between magnetic field and with a B and with an H, it's a constant. All right, so that's right. I was going to start out with the equation. And still did not write it down. I'm going to go grab the other notebook, because still, it's not one of those things that I commit completely to memory. I'm writing this up on the board, not that we will use it because it is calculus-based, but I'm writing it up just for sort of completeness here. And so when I write something like this is just saying for a really tiny change in the magnetic field, that is equal to, I'll just do the free space version, u naught over 4 pi dq, so this is some tiny bit of charge, v cross r over r cubed. So this is just one version of it. If I put it in 152 speak, delta v is equal to mu naught over 4 pi delta q v cross r over r cubed. Now there are 4 forms of this, and again, just for a completeness aspect, I have that r vector right there. That is just has a magnitude of r in the direction of r. So pretty much any vector can be written. I have some vector a that's just equal to a times whatever the direction of a is. Yes?
Are you multiplying those two fractions? Is that just
Yes, there's multiplication in there. One reason it's separated is that this is a constant, so sort of the constant in front. And since I can write my radial vector like this, this also is mu naught over 4 pi delta q v cross r hat over r squared. So one of the important things that I do want you to pull out of this is the fact that the magnetic field B does depend upon a charge. That's the Q. And it depends upon V, the velocity. And this vector R, well, vector R, if I have a charge Q moving to the right, and I want to figure out the magnetic field at point P, R vector R is this vector right here. It's a radial vector from where the charge happens to where the magnetic field is, or where we're trying to find the magnetic field. And the other bit in here is the fact that there's a cross there. This is a cross product. And what do you remember about cross products?
And multiply the perpendicular.
Like you mean it.
Multiply the perpendicular components.
Yes, indeed. And what is the direction of the result of a cross product? So if I have A going like that and B going like this, A cross B,
Is it right in between?
pardon?
Is it right in between them?
No. What is the direction of A cross B?
Is it out of the paper
Uh,
or in the paper?
into, yeah. Right hand rule, put your hand in the direction of the first vector, so A cross B, so that's in that direction. B is down like that, because I could have my hand like this, but I want my fingers so that they bend in the fastest direction to B. My thumb points in the direction of the axial vector, the result. So in this case, it would be into the board. But over here, if I did, well, my velocity is to the right. My radial vector is that direction. What is the direction of the cross product? Or what's the direction of the magnetic field at point P?
Into board.
Yeah, you got the velocity going this way and the radial vector down, so my fingers scroll that way into the board. Again, when you're doing this right hand, it's a right hand rule. So if I have a charge moving to the right here, what else could we say is moving to the right? And assume Q is positive.
The magnetic field.
But well, my question is, what else is going to the right? Magnetic field, I think we established, is going into the port here.
The electric field.
No. It depends. The electric field is going, if that's positive, away in all directions, so the electric field is going in every direction.
Is R moving?
Yeah, R would be moving along with Q. But think about the chapter then, or the test we have tomorrow. If I have a charge moving to the right, what else is moving to the right?
Current?
Yeah. I have current going to the right. Matter of fact, anytime I have a moving charge, I've got a current, so I've got my formula here for magnetic field, and this is known as V sub R.
I thought that said Bio sub R.
Yeah, the T's are not pronounced. One textbook said it rhymes with Leo the Tsar. So if I have a moving current here, I should be able to express this in terms of current then. And then what is, well, you tell me, what's velocity?
Delta X over, is that where we go? Delta X over, time?
Yeah. So I can replace that V with delta X over delta T, so I've got U sub naught over 4 pi delta Q times delta X, that's the vector, delta T across R over R cubed. I just recombine that right there and I get mu sub naught over 4 pi times the current times delta X cross R over R cubed, or mu sub naught I over 4 pi delta X cross R hat over R squared. So these are the 4 forms. So currents create magnetic fields, moving charges create magnetic fields. A moving charge basically is a current. Bless you. Now more on the cross product here. If I have a current moving to the right, so instead of looking at it as a single particle moving, if I have a current moving to the right, and I want to figure the magnetic field at point P here, so this one is into the board. In essence, I can pick any point and do a cross product, or another right-hand rule. If you're hitchhiking, you point your thumb in the direction you want to go. Well, in this case, you point your thumb, right thumb, in the direction of the current. Your fingers are in the direction of the magnetic field. So if I'm above my current, my magnetic field's coming out of the board. If I'm below, magnetic field's going into the board. So I could express the magnetic field out of the board up here, into the board down here.
So you're saying if it's going the other direction, your hand's gonna be like this, so these fingers tell you it's going into the board?
Going into the board on top, out of the board on the bottom.
Oh, like,
So into the board, out of the board.
But the current's going that way.
Well, he said if the
I was
current
saying
going the other direction. Yeah, in this case, out of the board on top, into the board on the bottom.
Are there other ways to tell other than using your hands? Is there math?
There's a cross product in there. We'll get to it. My right hand rule shows up a bunch. All right, let's talk about units. And other such things. Seems like that. Yeah. All right, this right here, this mu sub naught, is the permeability of free space. I suspect this one also is bad. Permeability of free space. The sub-zero is the free space aspect of it. Mu is just permeability. It has an exact value. U sub naught is equal to 4 pi times 10 to the negative 7th Tesla meters per ampere.
Tesla is in, what Tesla?
Yes. He may have died penniless, but he got a unit named after him.
What is that?
So-
The second one, it's T times.
T, Tesla meters per ampere.
So is that constant, just 1 times 10 to the negative 7?
Yes.
So 4 times.
And that's the value of mu sub naught in SI units. I guess technically what used to be called SI units. All right. So all this is great. I've given you a couple of calculus equations there. The rest of it is just deriving from that. Again, as mentioned last week, this is our second physics formula.
Now, the dB is the same thing as delta V.
Yes. The official difference from a math point of view, this is a change in B, and this is an infinitesimal change in B.
Oh, so the delta would be comparing like, okay, this number to this number, like this change, the
Right.
specific change, and then the dB would be like,
You're telling the difference between this number and this number, as opposed to between these two numbers.
why would it be better? Why would we use this one instead of this one?
Because if the magnetic field's not constant, then the change in this region here is different than the overall region here. This would find, if we found, it's like finding the average velocity versus instantaneous velocity.
Okay.
So this would be an instantaneous value.
Okay.
Okay, so enough of that. We're not doing calculus, so we need something that we can actually work with. So if I need a moving charge, let's say that I have a charge going across the room right now, heading from the front of the room to the back of the room. People over there, in what direction, actually wherever you are. So we got it going from here straight towards Giselle. What is the direction of the magnetic field that each person in here will feel? I see only a couple people doing right hand rules here. Ethan, right hand. The direction of the magnetic field on over here is what? So you're pointing to the back?
Yeah.
You're pointing to that wall?
Yeah, I'm pointing into me.
Well, yeah.
And over here, what are you thinking?
Right here, or towards the blackboard.
I'm gonna go that way.
Okay, Giselle?
In this way and then out that way.
Okay, so it is going like that. So I was picturing on this side over here, it'd be more down, and over here, more up. But what do you, Giselle, what are you feeling as far as the magnetic field goes?
Nothing.
Nothing. Because in that particular case, the velocity is right towards her. So this is Giselle. I have some charge here. Heading right towards Giselle, so that's my velocity. That's my radial vector. They're parallel to each other. So the cross product is
0.
0. So she's not going to feel a thing. Now, I have this charge moving straight towards Giselle, and Ibrahim decides that he's going to walk along with it. Well, let's just assume the particle's not moving very fast. So Ibrahim's walking with it so that it's constantly right here, or tip of my finger. What's the magnetic field Ibrahim's going to feel now? Why?
It's the same thing. It's just,
Same as what?
I would imagine it's the same as that because you're like right next to each other.
So you said the same as, oh,
Giselle.
Giselle?
Because we're parallel.
Not because you're parallel.
Because you're moving at the same time.
Because the velocity and the radial or the R are the same.
No,
The
no.
velocity between them is the same. Well, because this is the magnetic field, right? At the tip of your finger?
That's the charge.
Yeah, the point and the charge are moving at the same speed, same velocity.
Ibrahim
Yeah,
and the charge.
yes.
So what is the velocity of the particle according to Ibrahim?
0.
That's why magnetic field. Ibrahim would experience no magnetic field. So it's a really bizarre thing that if you're moving with the charged particle, you're not going to feel the magnetic field, but if he were sitting still, he would be feeling it. So magnetic field depends upon the velocity of the observer as well. Well, all velocity depends upon the observer, except for speed of light. Unit of magnetic field? Well, it's over there. It's the Tesla.
What is the test?
It is a unit of magnetic field.
But how does it relate to other units? Do we-
All right, a Tesla is equal to 10 to the 4th Gauss.
And that's in Gauss equals his own.
Yep.
Oh, that's so nice.
Does he have a
Gauss,
symbol for
one of the
his, or
greatest
is it
math,
just Gauss?
if not the greatest mathematician. Pardon?
Does he have a symbol for his, or is it just Gauss?
I think it's GA.
That's Georgia.
Not to be confused with Georgia.
So definitely not Soviet or US. I guess there's no Soviet Georgia anymore.
So what was he really saying about ohms?
Oh, actually, according to my notes here, it's just G. Not to be confused with giga.
What was, you were saying, how does the G relate to ohms? Gauss relate to ohms?
Oh, the,
I think he said.
I was gonna ask, like, how does? No?
you asked, somebody asked, how about Tesla, about how Tesla related to anything else? No,
That was me.
I'm slowly getting there. I don't remember what even you said.
Maybe.
Okay. If so, what's your comment? Now, how does this relate to anything else? So, the Earth's magnetic field, so, oh. Is approximately a half of a Gauss.
Oh.
So were Gauss is big?
How much do you feel the Earth's magnetic field?
I would imagine that's really big, if it's around the whole Earth.
No, that's the magnetic field can affect it. This affects compasses. It doesn't really seem to affect much else. So half a Gauss is not huge.
Do you think that's something like that? I think they have like a compass error form makes their GPS work.
Probably not a compass. I think it's just signals being sent back and forth, and a computer to figure out what it means because we're getting information from multiple satellites. The biggest magnet that we have produced is 27 Tesla. The biggest. So just give you some sense. That would be like at CERN or Fermilab, the huge physics research centers.
If that magnet was in this room, how much would it affect us?
I suspect that if we started moving, it would kill us. But I don't know for sure.
And I don't know if you know this, but how big, like, is that this size room kind of magnet?